Waveform patterns in vibration analysis, identifying key signatures for mechanical diagnostics. Waveforms and spectra, beating, amplitude modulation and gears, nonlinear clipped vibration, impacting, rotating looseness and classic looseness, belt damage, relating the waveform to the spectrum, pump cavitation, comparing vibration patterns and levels. Waveforms represent vibration amplitude over time, providing insight into how the machine vibrates moment by moment. They are essential for detecting transient events such as impacts, modulation, and beating that may not be obvious in the frequency domain. Spectra, on the other hand, display vibration amplitude versus frequency, revealing the sources of vibration and their severity. The waveform is the raw signal captured by sensors, while the spectrum is derived from the waveform using FFT. Analysts use both views together. The waveform shows the nature of vibration, steady, impulsive, modulated, and the spectrum identifies the forcing frequencies responsible for these patterns. For example, a clean sine wave in the time domain corresponds to a single peak in the spectrum, while a complex waveform with multiple components produces a spectrum with multiple peaks and sidebands. Understanding this relationship is fundamental for diagnosing machine faults accurately. Beating occurs when two vibration sources have similar but not identical frequencies. In the time waveform, beating appears as a pulsating amplitude that rises and falls periodically. This happens because the two signals alternately reinforce and cancel each other as they drift in and out of phase. The beat frequency equals the difference between the two original frequencies. For example, if two components vibrate at 10 Hz and 11 Hz, the beat frequency is 1 Hz, causing the amplitude envelope to fluctuate once per second. In the spectrum, beating is represented by two closely spaced peaks. If resolution is insufficient, these peaks may merge, making the phenomenon harder to detect. Beating is common when two machines operate at nearly the same speed or when looseness causes slight speed variations. Recognizing beating is critical because it can lead to high vibration levels during constructive interference, potentially damaging components. Amplitude modulation occurs when the amplitude of a vibration signal varies periodically due to another influencing frequency. In the time waveform, this appears as an envelope pattern where the vibration grows and diminishes in a regular cycle. In the spectrum, amplitude modulation produces sidebands around the carrier frequency, spaced at the modulating frequency. This pattern is common in gears and bearings. For example, gear mesh frequency, GMF, may be modulated by shaft rotation, creating sidebands at GMF plus or minus 1 order. Similarly, bearing defect frequencies such as BPFI or BPFO can be modulated by shaft speed as defects move in and out of the load zone. Identifying modulation is crucial because sidebands indicate mechanical issues like eccentric gears, misalignment, or bearing defects. The presence of multiple sidebands often signals worsening conditions, making amplitude modulation a key diagnostic feature. In gear systems, amplitude modulation typically involves the gear mesh frequency acting as the carrier signal and shaft rotation as the modulating signal. When a gear is eccentric or misaligned, the load on the teeth varies cyclically as the gear rotates. This variation causes the amplitude of the gear mesh vibration to increase and decrease once per revolution, producing sidebands around the GMF in the spectrum. These sidebands are spaced at the shaft rotational frequency, 1x, and may extend to multiple orders. The presence of sidebands around GMF is a strong indicator of gear-related issues such as eccentricity, misalignment, or tooth damage. Analysts use this pattern to differentiate gear faults from other sources of vibration. The waveform may show a repetitive envelope corresponding to the modulation, while the spectrum provides a clear frequency-based signature for diagnosis. Nonlinear clipped vibration occurs when a component's motion is physically restricted, causing the waveform to flatten at its peaks. This clipping introduces distortion, resulting in strong harmonics in the spectrum. The more severe the clipping, the stronger and more numerous the harmonics. Clipped waveforms are common in cases of looseness, rubbing, or mechanical interference where the shaft or component cannot move freely. In addition to harmonics, clipped signals may produce subharmonics or fractional order components, complicating the spectral pattern. Recognizing clipped vibration is important because it indicates mechanical constraints that can lead to accelerated wear or catastrophic failure if not corrected. Impacting refers to sudden, high-energy contact events within a machine, such as a loose part striking another surface or a bearing rolling element hitting a defect. In the time waveform, impacts appear as sharp spikes, often followed by ringing. In the spectrum, impacts generate broadband energy and a series of harmonics. Severe impacting can also produce subharmonics. Impacting is associated with faults like looseness, bearing damage, or rotor stator rubs. Detecting impacts early is critical because they indicate conditions that can rapidly deteriorate. Analysts often use high-frequency techniques such as enveloping to enhance the detection of impacting in bearings. Rotating looseness occurs when components such as bearing pedestals or couplings are not securely fastened, allowing excessive movement. The waveform shows repeated impacts and large amplitude variations per revolution. The spectrum displays rich harmonic families and often subharmonics like 0.5 orders. Both types of looseness are serious faults that can lead to severe damage if not corrected. Identifying these patterns helps analysts recommend corrective actions such as tightening fasteners or realigning components. Belt damage introduces unique vibration patterns due to slip, resonance, or misalignment. In the waveform, belt issues may appear as amplitude modulation or beating caused by variable tension and slip. The spectrum typically shows peaks at the belt frequency and its harmonics, often accompanied by sidebands. Belt resonance can amplify these effects, making diagnosis critical. Detecting belt damage early prevents efficiency losses and reduces the risk of catastrophic failure. Analysts look for characteristic patterns such as sidebands around belt-related frequencies and compare them with waveform anomalies to confirm the fault. Relating waveform patterns to spectral features is essential for accurate diagnosis. Impacts in the waveform correspond to broadband energy and harmonics in the spectrum. Modulation in the waveform produces sidebands around a carrier frequency. Beating appears as amplitude pulsation in the waveform and two close peaks in the spectrum. By correlating these observations, analysts can confirm fault types and severity. This combined approach ensures that transient events and complex interactions are not overlooked, providing a comprehensive understanding of machine condition. Pump cavitation occurs when vapor bubbles form and collapse within the pump, causing random high-energy impacts. In the waveform, cavitation appears as random bursts of high-frequency energy, while the spectrum shows a raised noise floor or haystack pattern. Cavitation can severely damage impellers and reduce pump efficiency. Differentiating cavitation from normal turbulence requires careful waveform analysis because both can produce similar spectral patterns. Analysts use time-domain data to identify the random, impulsive nature of cavitation impacts, confirming the fault and guiding corrective actions such as adjusting suction conditions or pump speed. Different faults produce distinct waveform shapes and spectral signatures. Comparing these patterns helps analysts identify the root cause of vibration. For example, unbalance creates a clean sine wave and a single peak at one order, while looseness produces clipped waveforms and multiple harmonics. Amplitude trends over time indicate fault progression, making trending an essential part of analysis. By using both waveform and spectrum together, analysts achieve a more accurate and reliable diagnosis, ensuring timely maintenance and preventing unexpected failures.